Let's continue with example number 3. Example number 3 reads, an electric fan is turned off and its angular velocity decreases uniformly from 500 revolutions per minute to 200 revolutions per minute in 4 seconds. Find the angular acceleration in revolutions per second squared, and the number of revolutions made by the motor in 4 seconds. So we just write down the given 4 seconds. Your initial angular velocity is 500 revolution per minute. Then down to the final angular velocity of 200 revolution per minute. You were asked for the angular acceleration and the number of revolution. So your angular displacement. So we start off by turning all your angular velocity into revolutions per seconds because the time is in seconds. So your initial angular velocity will become 500 revolution per minute. 1 minute is 60 seconds. So just cancel out minutes. So it will be 500 divided by 60 or 8.333 revolution per second. Your final will be 200 revolutions per minute. Then getting it in seconds, you'll get 3.333 or 200 over 60 revolutions per second. So we will use this in the equation. In the first rotational kinematic equation, angular velocity final is equal to angular velocity initial plus angular acceleration times time. We have all of this except for your angular acceleration. So rearranging this, transposing initial angular velocity, dividing it by the time, this will turn into final minus initial over time. Substituting the values, we get the final as 3.333 or just simply, so let's just write the decimal. Then the time, 4 seconds. Remember, this will be revolutions per second. This will be second, the one below. So it will just cancel out. It will be squared. So it will be revolutions per second squared. Take note that this is 200 over 6, then this is 500 over 6. So it's negative 300 over 6. Then times 4. This will be negative 300 all over 6 times 4 is 24. Or when we get the value of negative 300 divided by 24, 660. 60 times 4 is 240. So it will be 300 divided by 240. This will give us negative 1.25 revolutions per second squared. This will be your angular acceleration. For the angular velocity, we will use the third equation. And we can substitute the values. Initial is 500 over 6 revolution per second times the time of 4 seconds plus 1/2 times the angular acceleration that we just got, negative 1.25 revolutions per second squared. Then multiply it with the time squared. Substituting the values and simplifying, you will get so that's 2,000 over 60 revolutions plus 1/2 minus 10 revs. So 2,000 divided by 60, that will be 333.333 minus 10. So the answer would be 23.333 revolutions. That will be for example 3. Example number 4 reads, a record turntable rotates with a constant clockwise angular acceleration of 1.8 radians per second squared, and during the 5-second interval, it turns through a clockwise angle of 40 radians. What was the angular velocity at the beginning of the 5-second interval? So you can take we can use our angular velocity or angular displacement formula. Then initial times time plus 1/2 angular acceleration times time squared. We can solve for the initial using this equation. So substituting the values, transpose, and then divide by time, you'll get your initial angular velocity as negative 1/2 angular acceleration times time squared and divided by the time. Or we forgot the theta. So we write down the given first. Your acceleration is 1.8 radians per second squared. Time is 5 seconds. Angular displacement is 40 radians. There we go. I think that completes our variables. You can substitute. Get 40 radians minus 1/2 times acceleration 1.8 radians per second squared. Time is 5 seconds squared all over 5 seconds. Substituting the values. We get 3.5 radians per second. So this will be the angular velocity at the start of the 5-second interval. Take note that it was mentioned that it's a clockwise angle. So we will be, since we got a positive value, we will follow the same convention. Because when we used 40, it's positive. So when you get a positive angular velocity, this will be also clockwise. And for example number 5, a circular grinding wheel which is 0.15 meters in diameter starts some rest, and in 4.5 seconds it reaches an angular velocity of 120 radians per second with constant angular acceleration. You're asked to find the angular acceleration alpha and the angle theta through which the wheel turns in that time. So we're given the diameter 0.15 meters. You're also given the time 4.5 seconds and the angular velocity of 120 radians per second. So we were asked for the angular acceleration and the angular displacement. So we solved for the angular acceleration using the same given. The 120 is the final. It says it starts some rest, so the initial is 0. So we can use the derived equation earlier from the first rotational kinematic equation. Final minus initial over time. So the final would be 120 minus 0, both in radians per second over the time 4.5 seconds. So this will give us 26.66 repeating radians per second squared. In getting the angular displacement, we can use the third equation, rotational kinematic equation, initial angular velocity times time plus 1/2 angular acceleration times time squared. We substitute the values using the initial angular velocity, 26.6 repeating, so it will be 26.6. 7 radians per second squared times the time 4.5 seconds plus 1/2 this is the 26.667. The initial angular velocity is 0, so this is 0, so this will all be 0. I wrote the wrong value. Then the time 4.5 seconds squared, so it will just be 1/2 times 26.666 times the square of the time, so that will give us 270 radians. That will be your angular displacement. And those are our examples for rotational kinematics. Thank you for listening. Enjoy the rest of the day. God bless you.